Okay, so here so this is the last part of chapter 24. We just simply introduce the potential of a charge isolated conductor. So it says an excess charge placed on an isolated conductor will distribute itself on the surface. So we have already mentioned similar thing before. Within the conductor, there will be there will be no charges, and also no E field inside the conductor. But if there are some cavity, like just say if this is a conductor, and then there are some cavity, the 空腔 inside the conductor, then there will still be some charges. There will be charges. So the cavity is like a surface of the conductor. Yeah. So, but actually inside the conductor there will be no charge at all and no E field. Okay, so in that case, so it means that there will be no potential difference within the conductor because there are no E field, and if you try to really consider the integration of E dot ds, as much as E is 0 inside the conductor, then this line integration is nothing but 0. So there will be no delta V inside the conductor. And of course, outside the conductor, there will be E field. And of course, integrating a curve along the E field direction, or maybe not necessarily perpendicular to the E field direction, then there will be some value. Then you get some potential difference. Or if it is the other way around, over the conductor, the V is a constant. The V is a constant. So if you take the derivative, the E field is 0. So it'll be like this. So here is just consider if this is conductor, a spherical conductor, spherical conductor. The radius is 1 meter. So this r equals 1 meter. 1 meter. Okay, so it means that the charge, if there are some excess charge, then it will generate some E field outside, and there will be no E field inside. So if you try to go from here to here, if you already know the potential, so the potential inside the conductor sphere will be a constant. So we assume this voltage, and then of course it will decrease because this one is like a V equals K times Q over R. So it is proportional, inversely proportional to R. Okay, so in that case, or maybe we can call it capital R to distinguish between this R and that R. So so we call this one is R equals 1 meter. Okay, so this is proportional to 1 over R. And if you try to go from here to here, then you try to take the derivative. This is V, you take the derivative and minus sign. So here, take the derivative. This is a constant, so take the derivative will be 0. And then here, take the derivative for this function will be like, take the derivative of 1 over R will be like negative 1 over R squared, because you need to multiply, this is R to the negative 1 power. Take the derivative will be like a negative 1 times 1 over R squared. Okay, and then here you still have another negative sign, so it becomes a positive. So this one will be proportional to 1 over R squared, or inversely proportional to R squared. Or if it is the other way around, you try to integrate you integrate this function, and then it becomes this one. So suppose there will be an initial potential at the center, and the whole one you try to integrate along the radius. Then you integrate nothing because E is zero inside the conducting sphere. So you get a zero for this integration, but this is delta V. So we have all the way V inside the conducting sphere or spherical conductor. And then you further want to integrate this one. Of course, this is a positive value, but you need a negative sign here. So yeah, so you try to integrate this one, it becomes -1 over R. So it turns out to be something like this. Yeah, decrease. So here you just take the derivative, dx, and then you try to do the integration over the x or ds whatsoever. Okay, so this is a simple summary. Okay, for the electric potential and the E field. So up to now, we have studied 4 chapters from chapter 21 to chapter 24. Okay, so in chapter 21, we learned the Coulomb's law. So we have forces. So forces might be, even for high school student, you already know what is a forces, especially for the Newton's second law of motion, you should be very familiar with. And of course, here, starting from chapter 22, we introduced the electric field. And then in chapter 23, we're still studying the E field. Yeah, for the Gauss law, using the Gauss law to calculate the E field. And then in chapter 24, we also introduced 2 more variables, like the electric potential V and also the electric potential energy U. So we feel like there are quite a lot of equation, and maybe you will feel kind of confused. So here I just summarize these 4 variables, also the force, the electric field, the potential, and the potential electric potential. So actually you can see all of them have this factor K, so no problem for this term. And you can see some of them you have a Q1, Q2, or Q times Q0, something like that. Some of them doesn't have 2Q, only have 1Q. Here we have 2Q, 2Q, 1Q, 1Q. And then some of them have a R square in the denominator. Some of them have a R in the denominator. So of course, there are some relationship. So first of all, when you try to consider the first row, we have vector. This is force. Force is a vector. E field is also a vector. So in this sense, the relationship between the force and the field is F equals Q0E. We have learned it in chapter 22 at the very beginning. Okay, so F equals Q0E. So here, R square, R square. So the only difference is this Q0. We have Q0 here. We don't have Q0 here. So we multiply Q0 to here, and then it becomes the force. And then here, the electric potential and the E field have some relationship, as we have learned in this chapter. So actually, they look much more difficult than this one. But whatsoever, you really need to know what it means. So slightly earlier, we know the voltage difference or the potential difference is negative of the line integral of a E field over a path. So so actually it is like you try to integrate this one. You try to integrate this one to become here. So this is a polynomial. So you add 1 degree to R. So it becomes a single R in the denominator. Of course, there is a negative sign to cancel that negative sign. So all of them are only positive sign. Or the other way around, if you have the V you take the derivative, but in 3 dimensions. So it is a gradient operator. Negative the gradient of V will be the E field. Yeah, so you just try to take the derivative of this one. So this is r to the negative 1 power. Take the derivative will become negative r to the negative 2 power. So we have r squared here. And then here is a minus sign to cancel with that minus sign. Okay. And then here, the electric potential and the potential energy, or more specifically, the electric potential energy. Yeah, so they also have a similar relationship as F and E. F and E, you multiply Q0 to E and it becomes F. And here you multiply Q0 to V, it becomes U. So here you have all the way the same, except this is a Q0. We don't have Q0 here, so we multiply Q0 to the V, it becomes U. Okay. And then similarly, these two are similar. So actually, this is a force. This is the potential energy. So the potential energy is a scalar field. If you need to turn it to vector field, you take the gradient operator and take the minus sign. It becomes the force. It becomes the force field. Yeah. And then the other way around, if you try to integrate the force field over a path and then take the minus sign, it becomes the potential energy. Okay. So in mechanics, you might also know this relationship. Okay, so this is something to to relay all the variables we learned in the previous 4 chapters. Okay, so let's see some of the additional example. Additional example 1, I just skip it because later on, later I already included in the selected problem, so I just don't repeat it here. You can just check the selected problem. So we start from additional example 2. So here it says a plastic rod has been bent into a circle of radius r equals 8.2 centimeter. It has a charge Q1 uniformly distributed along 1/4 of its circumference, which is this part, Q1. And then a charge Q2 negative 6 Q1 uniformly distributed along the rest of the circumference, which is this part. Maybe I use yellow for this part. Yellow. Okay, so so with V equals 0 at infinity, what is the electric potential at center C of the circle? Yeah, actually this point. So if it asks you to tell him what is the E field at the center, it might be more difficult. But if you just need to calculate the potential at that point, it will be very, very simple. So it is like actually V equals K 1/4 pi epsilon naught, and then Q1 is 1.2 picocoulomb Q1. And yeah, of course, it tells you it is uniformly distributed, but even though it is not uniformly distributed, the answer will nothing be the same. So it is like Q1 over capital R contribute by this this part. And then for that part, it is negative 6 plus negative 6 Q1. And this is actually Q2. And then also over capital R. It also tells you that it is uniform distributed, but even though it is not uniform distributed, the expression will be nothing but the same. And of course, if it is uniformly distributed, it is also possible to calculate the E field, but yeah, it is quite complicated, honestly. So yeah, at least much complicated than this one. You don't really need to go for any integration because this is just a circle. So all the distance from this rod to this point are the same. The distance from here to here is the radius. The distance from here to here is the distance. So you don't really care about how does the charge are distributed. Yeah. So it is nothing but this, and then finally it becomes a 1 over 4 pi epsilon naught times negative 5q1 over r. So it is 8.99 times 10 to the ninth power, and then times negative 5 times q1. Q1 is here. 1.2 times 10 to minus pico. Pico is 12. Okay, so here R is 0.082 meter, 8.2 centimeter. Okay, so here the value is negative 2.3 volt. Negative 2.3 volt. What is the electric potential at the center C? Okay. So this is for part A, and then for part B, what is the electric potential at point P on the central axis of the circle at distance D? So here, rather than calculating the potential at point C, we calculate the potential at point P with this distance D. Okay, so here, yeah, still because this is the axis of the circle, so all the distance from the rod to point P are still the same because the radius doesn't change. And this side doesn't change also. This is a right angle triangle. So here you can regard it as a small r equals to r squared plus d squared, and then take the square root according to the Pythagorean theorem. Okay, so here r equals r squared plus d squared, and then take the square root. So it is 8.2 squared plus 6.71 squared. Okay, usually I suggest you to doing all the calculation in using SI unit, but yes, here because these are length, and also length, and then you can see take the square and then square root. So the SI unit doesn't really change. So just keep in mind that if we use centimeter for R and D, then this small r is still in cm. Okay, so we don't need to include 0.082 and then 0.0671 and then square, take the square root maybe. There are quite a lot of zero for the fractional part. So yes, so it might just might make you make mistake. So so just keep in mind that if this is centimeter square and then take square root, this is still centimeter, and then finally we can just calculate the v at point P. So it is 1 over 4 pi epsilon naught, and then times of course this is q1 minus 6q1, or q1 plus q2, which is q1 minus 6q1. So it is a negative 5q1 over small r. Okay, so this is nothing but 8.99 times 10 to negative 10 to the ninth power. Okay, and then times negative 5 times 1.2 times 10 to negative 12 over, this is 10.6 centimeter, 0.106. Okay, so this number is negative 1.78 volt. Yeah, it's slightly smaller value because this is a, lit, a little bit farther away from the ring. Okay, so I think this one is pretty easy. Okay, so the next one, The next one is a plastic disc of radius r. Is charged on the one side with a uniform surface charge density. So we have a surface charge density for the disk. And then 3 quadrants of the disk are removed. So this part are removed, only this quadrant is remain. So with V equals 0 at infinity, what is the potential due to the remaining quadrant at the point P, which is on the central axis of the original disk at distance D? This is the distance from the original center. Okay, so previously we already know that if this is a complete disk, it will generate the voltage like this without this 1/4 factor there. So this is the one for the complete disk. This is for complete disk. But here, if we only have a one quadrant and consider to this point, so for every quadrant, it will generate the same thing. It doesn't necessarily, it is one of the fourth area, but you need to consider the symmetric. So actually for this whole part, it will generate the same thing as this one. You don't necessarily mean this one generate the same potential at point P. They don't. But if you consider the whole quadrant with this one, they will generate the same potential at point P. And so as this quadrant and also this quadrant. So in this sense, we know that by symmetric, only 1/4 of this whole potential is generated by this quadrant. Okay, so the remaining stuff is also very simple because this is 1/4 and then sigma. Sigma is actually this one. Sigma is 7.73 times 10 to minus femto is 15 power. Okay, over 2 times epsilon naught is 8.85 times 10 to minus 12. And then times this square root of z. So here in this question, we don't have the same variable as this equation. So we need to slightly careful. So R and R should be the same. This is the original R for this equation, so no problem. So here Z equals D. So here we have Z substitute to be D will be 25.9 centimeters, 0.259 square plus R is 64 centimeter, 0.64 square minus this is Z, so it should be capital D. 25.9, 0.259. Okay, so this is nothing but 4.71 times 10 to the minus 5th volt. Okay, so this is the last sample problem for this chapter. So let me know if you have any question. If no, then we conclude this chapter. And then we will enter chapter 25.